Hey students, so in the last video we talked about the gauge maker's tolerances, and we talked about how to calculate tolerances, and then we looked at tolerances that fit into gauge classes. And I just wanted to show you something that I forgot to show in the last one, and that is this. Here is just a company's website. You can go out and you can find all kinds of these. But you can see here for a planar cylindrical gauge, they have standard sets of class XX, XY, Z, or ZZ gauges that you can go buy. These are ring gauges. You can also get pin gauges. You can get length gauges. All kinds of different sorts of gauges, and you can just go buy that set of gauges to the class that you wanted to use. And so what that does is it lowers the cost a lot, because you're not making custom gauges. And if you gauge a lot of different things, you go buy one of these sets and then you have the whole set. You figure out, okay, when I'm using the working gauge, I need to use the class double X gauges or the class Z gauges or whatever it is, and somebody can just go and pull the right pin or the right ring gauge from that set, and they can go and use it on the line. So that will be a lot less expensive. Now, you don't always want to do that, because with those you're typically buying the entire set. So sometimes you're going to want to just order a single gauge pin, or maybe it is a custom sort of shape, and so you need to order the custom item. What we run into, though, is a real challenge, because we have to give the gauge maker some tolerance when they're making this gauge. And the question is, how do we apply that tolerance? Because we know what size, if I'm making a go and no-go gauge set, then maybe it's a pin that fits in a hole, and I know the maximum size that that hole can be. And so I don't want the pin to be any larger than it needs to be, or maybe any smaller than it needs to be, whatever it is. And I have to figure out how to apportion the tolerance that I'm giving the gauge maker so that I get the gauge that I want to get. And so we're going to talk a little bit about some different strategies of doing that. Now, you've talked about these strategies some, I would imagine, and that's that you can apply those tolerances bilaterally or unilaterally, and then it turns out there are also two other standards for gauging, in particular a ring standard and a plug standard, which are a mixture of unilateral and bilateral. But if we're doing the bilateral system, what we're saying is our work tolerance zone is right here, and we're going to put the tolerance right on the edge of that, and we're going to give it a plus minus tolerance. And here is why that matters. Remember, this is for me to give to the gauge maker so that they can go and make the gauge that I need. And so, I tell them I want you to make the gauge to this size, to the work tolerance zone, but then we have to give them some tolerance. And so if I give them a bilateral tolerance, if they hit it right on the nominal, if they hit it right on the nominal, okay, well, that's fine, because that is a perfectly reasonable value for them to hit. But the problem is that they can, get this dimension to be anywhere in this half of the box over here, and it fits what I asked them to make. However, this is now too big a gauge, and it means that I may be allowing some bad products to go down my production line. But the alternative to this is that if I do a unilateral gauge and I give them some value, and they're probably going to shoot for the middle of the tolerance band that I give them, just because they want to make sure that they make the gauge within the tolerance band that I give them. Say they happen to hit the nominal value, then all of these items right here, any part that I've made that is between the value that they hit in my actual work tolerance zone, that is a part that I'm going to throw away, even though it is technically within the tolerance zone allowed. So the good part of this is I don't have anything that is outside the tolerance. So I'm not going to ever allow any bad product to go down the line, but I am going to throw away some good products that would not have to be thrown away. But I have to give the gauge maker some tolerance zone to hit. I can't give them an exact number because you can't make something to the exact number. Maybe you can do it once, but they would have to make a whole lot of these to get to the one that just hit that exact number. And even so, there will be some variation at different points on the part, and so they need a little bit of tolerance zone anyway. So I have to decide how to apply that tolerance zone. So let's look at how would we do that in the numbers, just to make sure that we understand it. We're going to do some of them. So up here in this set, I'm going to do bilateral, and down here we're going to calculate unilateral. And our tolerance zone here is 6 10,000ths of an inch. And so, but I have plus 6 10,000ths and minus 6 10,000ths. So that means that my total zone is 1.1 thousandths, 0.2. I don't know. It's hard to talk about these numbers, but anyway, 0.0012. All right, so then when I ask them to make something, if I ask them to make it like this, the upper edge of my work tolerance zone is going to be 1.2506. That is my nominal plus my tolerance. And then I'm going to give them the gauge tolerance. So this is my tolerance zone. So remember, my gauge tolerance is going to be 10% of that for a working gauge. So 0.00012, 120 millionths. And so up here, I've decided to do bilateral, and so I'm going to give them half of that tolerance above the limit and half below. So I'm going to say plus 0.00006. So there they have half the tolerance outside the zone and half inside the zone. If I'm doing the unilateral, I have the same tolerance zone, and so my gauge tolerance is the same, 0.00012. And when I give them the tolerance to make it, my nominal is the same, 1.2506. That is this 1.250 plus the 0.006. So that's the top end of the tolerance zone. But I'm going to give them plus 0 minus 0.00012. So what I've done is say you can have the nominal, or you can come inside by 0.00012 inches. All right. So when I look at what does this band give me? You know, what are the values that I would accept from the gauge maker when they send me this this gauge? On this one, yeah, 1.25066, and it could be that, or the other end of that tolerance is 1.25054. So that's 1.2506 minus the 60 millionths. But notice this one, 1.25066, is out. It's a larger number than my tolerance, so this is technically out of tolerance. That means I'm going to be passing some parts down the line that are not in tolerance, and so that is a bad thing. If I look at this bottom structure on doing this unilaterally, then what we would see is that, oops, I don't know where that came from. What we would see here is that the largest I can get is 1.2506, and then the smallest I can get is 1.25036, so that is the 1.2506 minus the 120 millionths. And so this is still within the tolerance zone, so I am never going to send a bad part down the line. But the problem that I have is that if the gauge maker, they are allowed to make this gauge to any size within this range. Let's say they hit the 1.25036 end. It's still a perfectly good gauge, but the problem is any part that is within this range is a good part, and I'm going to throw it away because the gauge says that it is wrong. Okay, so that just is a way to go about these, and we'll see on the next slide. There I've calculated both the upper limits and the lower limits just to see that. So which one of these do you choose? Do you choose to send bad parts to your customer? Or do you choose to throw away good parts and make every part that your customer buys be more expensive? Well, your organization has to decide what is the thing that is better to do. And that may depend on how important this part is. If it's a life safety part, you know, part of an aeroplane, something like that, you probably would not send out any bad parts. You would make sure that they were all good parts, and if you had to, you would throw away a good part rather than allow a part that was on the edge of the tolerance band to go out. If it's something that's not really critical, then maybe you would allow it to go. But one of the challenges with that is if you're allowing a part to go, you know, if you make something that is out of tolerance and you allow it to go down the line because you say, well, it's not really that critical, then the question is, why is your tolerance band that small? If you don't actually want parts to be within that tolerance zone, or it doesn't bother you, why would you allow that to happen? For some things, you can see for rings, they will be inside on both the large and the small side, and for plugs, they will be inside on the small side and bilateral on the large side. The reason that this happens somewhat is because of wear. Okay, so this gets even more complicated because not only do we have a tolerance when we make this gauge, but as we use the gauge, it's going to wear, and a pin will get smaller, a ring will get larger over time, and wear will happen. And so you have to figure out there how much you're going to allow the gauge to wear before you have to replace it. And then also, where are you going to apply that wear allowance? Are you going to allow the gauge to go further outside of your tolerance zone so that when it wears back, it will wear to where the point that you had for the bilateral? Or are you going to use a system like the unilateral system, and then because the thing may wear, you might throw away even more good product? And so that's a problem from a cost standpoint. So what do you do with this? Well, what you do is in whatever company you're in, your company needs to have a gauge policy, and that gauge policy should cover things like, are you using unilateral or bilateral methodology of applying to your gauges? It would also have things like, you know, what percentage are you doing for working gauges, inspection gauges, and master gauges? The 10, 5, and 1% are kind of industry standards, but they are not, they are rules of thumb. They are not a written standard. And so your quality plan would need to cover that kind of thing. You should have in your gauge policy, how are you going to measure your gauges and confirm that they are within the range that you need to hit? How often are you going to do that? Do you check every working gauge every day? Do you check it every shift? Do you check it once a week? Is it different for different parts? Because sometimes one part you make so many of that the gauges are going to wear a lot faster. How are you going to deal with wear? How much of a tolerance zone are you going, or a wear tolerance are you going to give in the gauge, and then how are you going to monitor that process? So is it just going to be that you change a gauge out after every 5,000 parts that it measures, or do you inspect that gauge weekly and throw it away when it gets to some tolerance? And so you need to have that. One thing that you would do is choose the materials of the gauges. So you may have less expensive gauges for things you don't measure very much, but when you go to a material that or a gauge that you're using all the time, you might go to a hardened alloy or go to something like tungsten carbide, which is very, very hard. The challenge of those, of course, is that those gauges cost more to make because they have to be ground. You got to put them on a surface grinder and grind them to just the right position, and so that costs more, takes more time, and your gauge will be more expensive. And you might develop a plan where you track gauges over a while, and from that tracking of the gauges, you then determine what is the wear rate of each different kind of gauge, and then you could apply statistics to it rather than having to check each gauge all the time. And so that would be the best thing that you could do. A lot of companies don't ever get there. Just because it's hard to keep that much data and deal with that much data, and it's often easier to just say, okay, we replace our gauges on this schedule. It would be much more cost efficient to have each gauge have its own schedule, but sometimes that isn't more cost efficient if you then have to hire somebody who's tracking every gauge and exactly when it needs to be replaced and such. So a computer system can help you with that a lot. If you have people doing it, it's pretty expensive and pretty complicated. All right, so that is how you choose, or a sort of a broad overview of how you choose gauge maker tolerances so that you can make your gauges, and then how you choose to apply those tolerances to the gauges that you're making. All right, see you in class.